Hello and welcome. Uh, my name is Bob Dillmore. I'm a research engineer at the National Energy Technology Laboratory in Pittsburgh, and I'm the technical director of a project called the National Risk Assessment Partnership. Um, NRAP is a 5 national lab collaboration, bringing together experts from across these labs to address questions related to risk and associated with large-scale geologic carbon storage. Today we have, it's my pleasure to introduce Dr. Denise Templeton, who's a research scientist in the seismology group within the Physical and Life Science Directorate at Lawrence Livermore National Lab. She's also a member of the NRAP Induced Seismicity Risk Management Team, and she will give us an overview today of the recommended practices report for managing induced seismicity risk associated with geologic carbon storage. I'll let you get started. Thanks very much.
Great, thanks, Bob. So hi, everyone. I am Denise Templeton. And as Bob was saying, today I really wanted to talk about our recommended practices for managing induced seismicity associated with geologic carbon storage. And, as Bob was saying, this project was developed as a collaboration from lots of different researchers from various laboratories. Martin Schoenball, formerly from Berkeley Lab, Kareem Leland-Bachman, Bill Foxall, Yves Guglielmi, also from Berkeley Lab, Kayla Kroll from Lawrence Livermore Lab, Jeff Burkhart from PNNL, Bob from NETL, and Josh White from Lawrence Livermore Lab. So these recommended practices are in support of DOE's carbon storage program, and they have a larger aim of improving carbon storage efficiency, reducing costs, project risk, decreasing uncertainties, trying to identify ways to ensure that the operations are safe, economically viable, and environmentally friendly. So NRAP has developed recommended practices which are focused on quantifying and managing subsurface risks, to support the implementation of these, safe and secure large-scale geologic carbon storage projects. And today I'll be focusing on the induced seismicity recommended practices in particular. So induced seismicity, just as a background, it's like once we inject fluids into the ground, we can change the stresses and the pore pressures in the subsurface, thereby causing, potentially causing induced seismicity. These can occur either through the creation of a new fracture, through the injection itself. If there's a fracture already within the reservoir, that could be reactivated. It could be induced seismicity can occur, around the reservoir if there's any physical expansion of the reservoir, for instance. And it could also occur distant, away from the reservoir by altering the stress field and the pore pressures of the rocks outside the reservoir. So our big question was, how can we systematically address the induced seismicity aspect of geologic carbon storage? And so we decided to create these induced seismicity recommended practices. So again, this is a multidisciplinary team. Our overarching goal is to help facilitate the successful deployment of domestic geologic carbon sequestration projects. So we created a set of 7 recommended, a set of 7 steps for the recommended practices, which would proactively address and mitigate potential problems with induced seismicity due to this subsurface injection of CO2. And, from the start, we saw this as a living document. It's like we want to keep on updating it and keep on having like all the new results in this document. And so the audience is, subsurface injection operators, regulators, the general public. We wanted to make it as accessible as possible, even though we are dealing with, a very technical issue here. And the approach we took was both technical and non-technical. Project-wide and project lifetime. So from the very beginning considerations to through closure, post-closure. The base methodology that we're using here is similar to the 2012 DOE Geothermal Technologies Office protocol for addressing induced seismicity associated with engineered geothermal systems. So here are the 7 steps to address and mitigate induced seismicity. These recommended practices are, and what we're advocating here with these recommended practices is a very broad-based, multidisciplinary approach. These steps are essentially a framework that outline general actions, methods, and procedures that represent the current state of the art in induced seismicity risk management. But we don't prescribe specific tools or specific codes or specific parameters. We know that each carbon storage project is going to be unique. It's going to require a custom approach. But these science-based recommended practices can be used as a starting point on which to build a site-specific induced seismicity risk management plan. So these steps encompass the entire life cycle, as I said before, from initial consideration to development and operation to post-closure. So we start with step one with like the preliminary seismic risk screening evaluation. We continue through outreach and communication recommendations, ground motion threshold recommendations, collection of seismicity data, hazard evaluation of both natural and induced seismic events, risk-informed decision analysis, and operational management of the induced seismicity risk. So for step one, the preliminary seismic risk screening evaluation, our goal here is to create simple methods and acceptability criteria that can be used to evaluate the merit of candidate sites. Our result is, a preliminary assessment after this step is completed, for a go, no-go feasibility decision. So how do we do that? So the first part is, just do a review of local, state, and federal laws and regulations relevant to seismicity, see if there's any red flags there. Do a review of prior cases of injection-induced seismicity in comparable operational and geological settings. So ideally, there would be other geologic carbon storage sites nearby, but that's probably not going to be the case, especially in the beginning of this process. So are there any other types of fluid injection projects that have been occurring in the same reservoir or nearby? And also looking at regional scale and our operational trends. So what I mean there is, there are observed trends of seismicity in Oklahoma, for instance, connected to wastewater disposal in the Arbuckle group. But alternatively, there's been a relative lack of injection-induced seismicity in the Williston Basin in north central United States, where large-scale fluid disposal is also occurring. So just taking into account these larger regional trends will be important in this step one, to see how comfortable the operators are in proceeding. We also need to create an initial estimate of the region of concern. And there are NRAP tools available which can help identify this preliminary region of concern, like the ground motion prediction for potential induced seismicity tool. It can use some basic information to produce an estimate. Now, again, this is just a first order approximation of the ground surface area that could be negatively impacted by induced seismicity. We know in actuality that, this region of concern is governed by many factors, the reservoir size, local geology, the in-situ state of stress, for example. But, here in step one, we're just doing a rough estimation. And to get this, a preliminary determination of the potential maximum magnitude induced seismic event is going to be necessary, where we might expect these events to be occurring, and an estimate of the ground motions associated with such an event. Then we can estimate the ground motion threshold above which negative impacts would occur. So within that region of concern that we have, preliminarily identified, what are the potential impacts to the local community? So potential impacts might include, population centers, looking at the building and infrastructure inventories. So for example, where are the residential buildings, commercial buildings, historical buildings, essential facilities, transportation lifelines, potentially hazardous facilities like chemical plants or unreinforced masonry buildings. We also want to consider, social disturbances, nuisance effects, economic disruptions. So those will be tied to, where the population centers are as well. And then we need an estimation of the magnitude of the potential impact. So for example, if we're looking at like a particular type of event or one particular building, that's common in the area, like would there be no damage or cosmetic damage or structural damage if a average size induced seismicity event were to occur? And again, there's a little asterisk there as to what would we consider an average size event, and that again would be site specific. What would happen if a maximum magnitude induced seismicity event were to occur? Again, what would the damage level be, or would there be any damage? And we also want to consider the effect of natural tectonic events within the region, even at this early stage. And part of that is, it's like it would be good for the operator's general knowledge, as well as, the local stakeholders, so that they can do a preliminary comparison between potential impacts due to natural tectonic events and potentially induced events, because they've kind of already accepted the risks for the natural tectonic events, so they're able to rate them. We also want to make an assessment of the local stakeholder risk tolerance. Do they have high risk or do they have low risk tolerance? Like that would be an important part of step one. And, with all of this information, then we can put it all together and make an integrated assessment of the overall preliminary risk assessment of the planned operation, based on, some combination of the factors above weighted by the local stakeholder risk tolerance, for instance. And this is definitely going to be site specific. So we can, if, for example, there's no people in the region of concern, there's no infrastructure. After some preliminary assessments, no significant faults were identified. Maybe that would be a green, and there would be no cause of concern to proceed with planning. So that means further investigation. On the other hand, at this level, at this preliminary level, if there is a red flag, for instance, like a large event was identified in some of the preliminary geophysical studies, or there is a large population center, or there is a low local stakeholder risk tolerance, and maybe that would push it up to the red, and then you can go on to another site to consider. Okay, so step 2 is outreach and communication, and we put it almost at the beginning of this of our 7 steps, because we feel like it's really important. So the goal here is to create an induced seismicity component to a project's general outreach and communication program, to facilitate communication, to maintain the positive relationships with all stakeholders. The result we're hoping to accomplish here is to create a program that would engender long-term stakeholder support for the project through information exchange and trust. So this starts off with a broad-based participatory process. So knowing, early on, identifying who the stakeholders are. That could be, local communities, governmental agencies, tribal governments, public safety officials, regulators, anybody who comes up in that process of people who need to be involved should be reached out to. There should also be general stakeholder agreement that the status quo is unacceptable. And this really depends on how the public education and outreach events are going. So we want to be able to articulate, both the broad societal goals, identify any local stakeholder needs that can be addressed with the project, but also include, perhaps information about, what the consequences are of not moving forward with the project. So again, with the broad societal goals, we have climate change, for instance. And there should be conversations, about how this can help both at the wide, societal level, but also at the local level. There should be stakeholder consensus of the project plan. So obviously this is going to be an iterative process. All stakeholders should feel like they have the opportunity to communicate their comments and concerns about the project plan. Everyone should be open to alternative approaches, but also include in the conversation, both short-term and long-term implications of those various options. The operator needs to gain an in-depth understanding of the concerns of the local community. And, for the other stakeholders, they need to be provided with, general information about the project, like what's motivating the project, visualizations of the project, understanding who is on the team. In terms of the seismic information, the history of induced seismicity in geologic carbon storage projects or other fluid injection projects should be described, talking about the similarities and differences between induced seismicity and natural tectonic events. There should be a discussion of potential risks to the community, but also the risk mitigation strategies that the project is going to be putting in place to make sure that there aren't any risks that go above, what the stakeholders are willing to accept. There should be a discussion of the seismic monitoring system, and most importantly, where to get more information. So there should be a communication that stringent safety standards are being met, and this is going to again feed into the risk-based mitigation plan. So this is where we're going to describe, in the plan what safety standards are going to be met, and then communicate that out to the various stakeholders. There should be a commitment on the part of the project to fully address all negative aspects. And, again, that should be, within the risk-based mitigation plan, should be written down ahead of time. Everybody will agree to it. And this is not a one and done. It happens at the beginning and then you can forget about it. This is something that's going to be continually needed to be looked at, developed, maintained, to maintain stakeholder trust. So there needs to be a team who has specialization in this area and is part of the main team. Okay, so step 3 is ground motion threshold. The goal here is to determine site-specific ground motion thresholds that would minimize nuisance and damage risks to the local community. So the result here is the development of criteria for monitoring, risk assessment, and the operational management plan. So the first part is to review any existing standards and criteria. So the first level would be, any federal, state, and local standards regarding ground motions, those should be reviewed. We should also review the limits of human perception of ground motions. And there's a table on the bottom, for instance. There should also be a review of ground motion levels for cosmetic and structural damages for different building types. This was done in step 1. I think here in step 3, what's really needed is an on-site evaluation. So we need an assessment of the site-specific conditions. There needs to be a more complete assessment of the buildings and structure types that are actually in the region of concern. There needs to be a more complete assessment of special activities or equipment, for example, special medical equipment or special industries that require, some kind of non-vibrations to be occurring. And there should be an assessment of existing environmental vibration conditions to see what is already being accepted by the community. And then at the end of this, there's going to be a designation of site-specific ground motion thresholds. We suggest at least 4. So 1 would be the limit of human perception. Ideally, it would not go above this level. Also the level of cosmetic and structural damage, an identification of what the threshold would be to cause the destruction of, special activities or equipment within the region of concern, and if there's any applicable regulations, those should be taken into consideration as well. So step 4 is looking at the local seismic monitoring. So the goal here is to create a seismic network, an information database for induced seismicity mitigation and reservoir management purposes. The result, we hope to have seismic data to aid in the design and operation of the overall project. We're going to have to figure out where the optimal station locations are going to be, how that could help identify where, maybe the well locations should be, feed into the seismic hazard evaluation and the operational management plan. So the first part is looking into existing seismic activity before operations. So we would be looking at earthquake catalogs, historical records, fault maps, paleoseismic studies. looking at previous induced seismicity in the area, and gathering new seismic data. And the reason we want to gather the new seismic data is because, especially in the U.S., the NEIC has a goal of detecting and locating events in the U.S. that are greater than magnitude 2.5 to 3.0. And this background level of monitoring, although it's good for overall hazard assessment, it's not actually sufficient for monitoring induced seismicity, where routine detection of events should be considerably smaller. Additionally, the new seismic network should be in operation for at least a year, although at a minimum 6 months. And this will help determine when we get into the post-closure period, what the background rate is. Okay, so we're also going to have to determine what the seismic monitoring network is going to be looking like. If we have an area, if in this particular example, if the reservoir is in red, what would our surface and our borehole seismic network need to be in order to identify events, above a certain magnitude. And this can, and the seismic monitoring network should be designed to detect and characterize seismicity down to magnitude 1, maybe with a 2 sigma location accuracy of about 0.5 kilometer in the horizontal direction and 1 kilometer in the vertical direction, for all the events that are going to be happening within the subsurface. And again, there are NRAP tools to help with this monitoring design phase, such as the passive seismic monitoring tool. There should also be discussions about the seismic monitoring operation. What's going to happen before, during, and after injection operations? What are the data processing requirements? Again, this is going to be part with a conversation between both the operators and the other stakeholders. There should be a conversation about what data and data products are going to be available and an archive plan moving forward. Another component for the local seismic monitoring part is, public reporting and engagement. What data and data products are going to be made publicly available? Is there going to be near real-time reporting? Is that going to be feasible? And, there's definitely going to be annual reporting. What should be included in the annual report? So for step 5, this is, step 5 is going to quantify natural and induced seismic hazards. The goal is to estimate the ground shaking hazard due to natural and induced seismicity at a proposed site. The result is going to be the evaluation of the potential increase in seismic hazard due to the site activities. So we first start off with determining what the baseline hazard is from natural seismicity. And this is, for this, we're recommending a site-specific probabilistic seismic hazard assessment, or PSHA. For this, one of the first things we're going to need is a database of potentially damaging earthquake sources that are occurring within or near the area, including fault-specific sources and any aerial sources. Also, the spatial, temporal, and frequency magnitude distribution models for each of the seismic sources. So the spatial distribution models for the earthquake sources are needed to calculate the distance distribution between potential future events and the site. The earthquake recurrence models, or the frequency magnitude models, they provide information on the frequency of recurrence of the seismic events of various magnitudes, between a pre-selected minimum magnitude of an earthquake of concern up to a predetermined maximum magnitude that each source is considered capable of producing. And the maximum magnitude is a key parameter here, but it's often poorly constrained. So other information that we need is also a site-appropriate ground motion model for earthquakes as a function of at least magnitude and travel path, and local site response information. For example, geological, geophysical, topographical information. And local site effects can dramatically influence the amplitude, the duration, and the frequency content of local ground shaking, at a particular site. So this should be incorporated into the model whenever possible. And lastly, we can take the above inputs and develop seismic ground motion hazard curves that show the estimated probability of exceedance per time, typically annually, on the vertical axis that we can see on the right, and for different levels of a selected ground motion parameter. So, for example, like acceleration or peak ground velocity, and that's on the horizontal axis. So generally, what we'll see is that low levels of ground motion are expected to be exceeded relatively often, so they have a higher probability. Small events will happen more frequently, while higher levels of ground motion will be exceeded rarely, so they would have a lower probability. So the probabilistic seismic hazard assessment results can also be shown in map view, which is often easier to read, although slightly less rigorous since they're based on interpolations between the actual derived hazard curves. Hazard maps, however, present a more complete overview of the hazards and are definitely easier to comprehend for a more general audience. So once we have the natural seismic hazard assessed, we need to consider what the additional hazard is from the induced seismicity. And so for this, we need a probabilistic short-term ground shaking hazard forecast. So similar, but slightly different for the natural hazard. So for instance, the earthquake sources, differences from the PSHA for the natural sources arise when that slip on the faults and fractures may be induced by the injection program, as opposed to normal in situ stress from tectonic sources. The spatial, temporal, and earthquake recurrence model, it's like a range of a range of minimum maximum magnitude events of concern when considering the natural tectonic hazard and the induced seismicity hazard can happen, but it's like the two groups, if there are two groups doing this, really need to be in conversation. So this is an easy sticking point. How can we make sure that the analysis is consistent, between the natural tectonic hazard and the induced seismicity hazard? And we should consider expanding, beyond the stationary Poissonian model, because natural or induced seismicity, varies in space and time. So for the site-appropriate GMMs, they should be the same or similar, although this is a big technical ask. And again, the output is going to be, hazard curves and hazard maps. Different from the natural hazard, for the induced seismicity hazard, updates should be done at least annually or more frequently as recommended. And again, this is because of the changes to the anthropogenic source that will be expected. So step 6 is a risk-informed decision analysis. So the goal here is to do a rigorous quantitative estimate of the time-dependent induced seismicity risks associated with the design, operation, and closure of a geologic carbon storage site. The result here is a determination if the potential future negative effects of the operation are within the tolerance range of the stakeholders. So we start with, in order to determine what the seismic risk is from natural seismicity, we'll take the seismic hazard analysis from the natural seismicity that we had done in the previous step. We'll include the identification of the people, the assets, and activities that could be adversely affected. So again, this is something that we had done in step 3. We can, build upon that. So looking at the population centers, looking again at the assets and activities, are there any special equipment? Are there, football fields? Just looking at the socioeconomic impact, looking at the distribution and the type of buildings and infrastructures, what are the building codes that are in the region of concern, and any pre-existing conditions. So for this, the vulnerability potential of the people, assets, and activities within a particular site should be quantified through a vulnerability assessment of the area, and this can be done in various ways. For example, one can focus on the anticipated repair costs, or on the probability of exceeding a given damage stage, if they're going to be slight damage, moderate damage, extensive damage, as a function of increasing ground motion intensity. And the results themselves can be provided in a variety of ways as well, and which one is quote unquote best for a particular project, that will be determined at the site level by all the stakeholders. So once we get the risk, the seismic risk from natural seismicity, we also want to include what the risk is from induced seismicity. So again, we'll take the seismic hazard results from the previous induced seismicity analysis. Again, the people, the assets, and activities will all be the same because the region of concern will be the same. The actual vulnerability potential might be a little bit different, but the way that we quantify the seismic risk will be similar. So with that information, the seismic risk from natural seismicity and induced seismicity, we can start making a risk-informed decision analysis. So this, again, is going to be an iterative process. So project planning should occur alongside the risk-informed decision analysis. From the very beginning, changes to either where the wells are located or to the injection plan should be occurring. And as new information becomes available, this project planning should be updated. And always there should be a clear description of uncertainties. So step 7 is the operational management of induced seismicity. And so the goal here is to create a site-specific real-time plan to monitor, assess, control, and mitigate the risks associated with induced seismicity. And the results will be a clear set of procedures known and approved by all of the stakeholders ahead of time to be followed in the event that certain seismic thresholds are reached. So the induced seismicity mitigation plan should be in place before any injection operations begin. The framework could be based on a traffic light system protocol like this one here. This is probably the most widely known and visually easy to read criteria. So these traffic light systems communicate the status of the project, with the color level. They specify predefined actions that should occur in order to prevent larger magnitude induced events from occurring. And it prompts the operator to consider changes to the operations. So these traffic light systems typically have 3 or more response levels corresponding at a minimum to, a continuation of normal operations, which would be green, heightened awareness and revisiting of injection operations due to, some concerning observed seismicity or trend. So that would be yellow. And also a clear indication of when injection should stop due to some unacceptable observed activity. And a traditional traffic light system typically defines the actions to be taken, based solely in response to some observed criteria. So, for instance, an event larger than a magnitude X, you would automatically go up to the next level. One new area of research is looking at adaptive traffic light systems. So in this case, there would be some proactive determination of how to determine when to change when to modify the operations and enhance communication. So, for example, if we feed the real-time monitoring system into the traffic light system, we can do rapid hazard analysis in real time and a rapid risk analysis again in real time, and feed that into our determination, our threshold criteria, and our actions. Then we can determine what level that would be. Again, that would be site specific, but we can determine the threshold criteria at which point further actions and modifications and communication with local stakeholders would happen. Another part of the operational management plan is to have an expert panel. So this panel would provide evidence-based information and recommendations pertaining to the induced seismicity risk. Excuse me. This would be a forum in which the operator, the regulatory agency, other stakeholders, and independent subject matter experts could monitor and assess the induced seismicity and develop recommendations for any changes. And this is especially important when we might have overlapping regions of concern to make sure that there's third parties who are involved. We also explicitly state that there should be an early evaluation period. So this would be the first year of the injection. This is a time when the relative changes in pressure and stress may be at their greatest, and also the greatest time when incomplete knowledge of the subsurface is happening. So as time goes on, we're going to learn more about our reservoir. But in this early evaluation phase, we should be especially cautious. And injection operations should be gradually increased, and any increases in the planned injection rate should be recommended by the expert panel. There should also be a post-closure evaluation. So monitoring and analysis should continue until there's stabilization of the pressure and stress perturbations to a steady state value, and that there's a clear demonstration that the seismic frequency magnitude behavior is approaching baseline tectonic conditions. And what exactly that is going to be, again, should be done at the site-specific level. One important aspect that's going to have to be discussed ahead of time is liability and insurance. How are individual homeowners, for instance, and individual businesses going to be compensated if there are any damages caused by induced seismicity? This should be included and discussed within the induced seismicity mitigation plan as the last level of indirect mitigation. All of our steps here are aimed at making sure that there are no damages at the surface. But there's always a chance, there's always a risk, and so this is the last level of indirect mitigation. Also, especially if there's a shared region of concern, there needs to be a plan for how the damages are going to be determined, and like how that is going to move forward. So in summary, so the goal here is to do a set of recommended practices. We have put this into a document describing our 7 steps to deal with induced seismicity in geologic carbon storage projects, to enable the safe and economic implementation of geologic carbon sequestration with respect to induced seismicity. So there are other recommended practices out there that deal with other aspects. The document is online, and our path forward is, we do want to revisit this, the recommended practices every few years to include any recent lessons learned, any case studies, integrate any other best practices based on new research and development. So this is an active area of research. We want to make sure that we are keeping this document as fresh as possible, so that it will be of as much use as possible to to the operators and to the stakeholders. Okay, great, and thank you. I just want to acknowledge that our sponsors. Okay, thank you.
Thanks very much, Denise. We do have time for questions. People can either unmute if that gets chaotic. Since we have a lot of people, we may take them in the chat as well. So I'll stop and see if there are any questions.
Fred, I notice your hand has been up.
Yeah, I have. First of all, it was a great talk. Thanks for all the good information that you conveyed. I have a question on, roughly speaking, I understand it's different for different sites, but roughly speaking, what is the typical level of effort involved in doing a reasonably good induced seismicity risk analysis?
That's an important point that we were considering, and that's why we especially decided to take that graded approach. For the step 1, if we can think of this in terms of dollar signs, step 1 would be, $1. The full analysis is probably going to take, $3 or $4 signs to do that. and we want to be as conscientious as possible. So, in the beginning, it's like, how can we identify early on what the red flags, if there's any red flags, in which case, we can, put a site to the side, after that evaluation, and then, try to figure out what are better sites to be pouring some resources in. And the truth is, it's like we might be going through the steps, and we might, after step one, we might identify a place that seems, reasonably risk, with low risk. But at some point, we might again find something within, step 5 or step 6, where the risk goes above what the stakeholders are willing to accept. And we can have conversations at that point, and that's why, step 2, which is the outreach and communication plan, is so important, so that, can there be some modification to the plan? Can there be some adjustment to, how it's being implemented or how it will be run, or the duration of, can there be any modifications that can lower the risk to an acceptable level?
Yeah, I actually have a reason for that question I asked, and that is there is some concept of transfer learning. And the question is whether a few past induced seismicity analysis done on other sites could be used to create some sort of a database and use transfer learning to reduce the cost of doing this whole risk analysis for induced seismicity.
Yeah, I would say definitely. And that would be the most ideal case, if there could be a sharing of the data, sharing of the results to some extent, obviously. And in that case, if you have, regional knowledge or, even reservoir knowledge of what's going on, if it's a really big reservoir, can we share that information so that, we can make an informed decision with less dollar signs or smaller dollar signs attached, to that analysis? We don't have any power to force people to share information, obviously, but we can make that recommendation.
Thank you.
Thank you.
There's a
Denise, nice talk there. Just one question for me. Does the framework also look at special cases of what we call microseismicity?
Special cases of microseismicity?
Yeah. Because we know that usually during the site screening stages of most geologic carbon storage sites, the big issue of the year is, can we induce any big major earthquakes? So you always avoid that as part of your site selection, right? So they practice that. Oftentimes the issue is around the microseismic events and how the public perceives that. So we in the community, from a technical perspective, well, microseismicity is nothing, but the general guy who doesn't understand that might see that, oh, it's an earthquake. No, it's not an earthquake. It's something. How does the framework address any specifics around microseismicity and how you communicate that?
Yeah. So if I understand your question, you're talking about seismicity that isn't going to be damaging to either the cap rock or to the facilities or to any of the facilities of the operator or to any people on the surface. But if it's noticeable, by the people, for instance.
Correct.
So, and so that's one of the items that we definitely want to take into consideration, and we specify, in our recommendations. It's like when we look at the risk, we need to take into account not only, for these vulnerability assessments, we're not taking into account just minor damage or moderate damage, but taking into account nuisance risk, and that's actually definitely an area of active research. How can we quantify that? That is, something that we need to take into consideration because all the stakeholders need to be on board with the project plan. And they all need to be able to see benefit from, from this project, both on the grand scale and, at the local level. And they need to feel like, they are part of the solution here, and that, there is going to be a synergy between, like the local population and the project itself. So yes, that's definitely something that we need to avoid. We specifically, talk about that. Again, with the caveat being that, those vulnerability algorithms are in their infancy right now, I would probably say, although active region of research, and definitely, yes, need to be incorporated.
Our first question in the chat comes from John Templeton. Can you speak to how these recommendations have been and/or are being received by ongoing CCS projects and regulatory bodies?
Right. So no relation. So these just came out, I would say, in December. So we are in an advertising phase, I would say. So we are meeting with some folks, with some operators, for instance, to discuss this in a little bit more detail. I think that's important, especially when we're talking about something, a framework that's relatively new. Regarding, regulators, that was actually something that we discussed at the beginning of this project. We wanted to be policy regulation agnostic to a certain extent. We wanted to focus specifically on what the science was telling us. Both like the social sciences and the and I guess the hard sciences, I would say. Like, what are the best practices there, and not take into consideration, what the regulations are saying. So we haven't, to date, really had a lot of discussion with them, I would say, one-on-one. Like, we've had avenues where, such as this one, where, obviously there's regulators in attendance, and so they're hearing about what we're doing, but we're not really integrated, per se. And that was kind of a deliberate action on our part.
From John Hunt, what is the anticipated lead time to start this process ahead of starting a CCS project?
That's a great question. So I would say this would be happening at the same time as all the other analyses that need to be going on. So it's not that we're necessarily adding time to the original time frame. Ideally, it would be happening at, concurrently, like all of these analyses, all of these seismic analyses would be happening at the same time as the other analyses, So at some point, there needs to be analysis about, like what the porosity is, what the connectivity is, and what faults might there be, how's the cap rock, like what is the integrity of the cap rock. So, all those very important items are not necessarily discussed in this particular recommended practices, but they're kind of assuming to be going to need to be happening at the same time. And honestly, it's like, actually, this is probably going to be happening after the start of some of those investigations as well, because we do need some level of information on the site to, start making these preliminary assessments in step one.
Sanjay's question came next, and then Sherilyn and Jorge. From Sanjay, are there good case studies of CCS projects that have implemented all the 7 steps recommended for assessing induced seismicity risk? Are there any publications in this area?
Right. So for induced seismicity, no. For induced seismicity, specifically in carbon storage, no. But I would say yes for induced seismicity in engineered geothermal systems. So those particular, the Geothermal Technologies Office did a similar methodology, and those protocols came out in 2012, and several projects have used these types of 7 steps. So obviously not exactly these, because there are differences between engineered geothermal systems and geologic carbon storage systems that we took into account for this particular methodology. But, you know, as of right now, I have not heard that anybody has completed from start to finish, even at a small scale.
Sherilyn, your hand came up next.
Hi, thanks. Hi, Denise. I'm a big fan of this public engagement aspect of it, because I think that goes a long way to getting people to not be afraid, and once they have buy-in, even if they don't feel it, they might think they feel it, right? Unless you kind of educate them. But the question I had was about the USGS hazards map, right? So you showed the natural hazards map, and I know that the USGS at one point produced a map for induced seismicity, but then they kind of stopped doing it because they weren't happy with the methodology. And I wondered if you were aware of any more progress on that, because you did say the induced seismicity has to go on top of that, but I don't know what the methodology is.
Yeah, that was something that was unfortunate, I think, in my opinion, that they stopped that and haven't been able to restart. When we first started this project, you know, their last induced seismicity, you know, like short-term induced seismicity hazard map had just come out. And, you know, in the course of, you know, writing this up, we learned that they weren't planning, that there were no plans to continue that, you know, for the immediate future. And so, you know, we kind of reworked it within these particular recommendations to, you know, remove that part, you know, like remove discussion of the USGS short-term hazard assessments moving forward. I don't know. I hope that they go back to it, but I don't have any special knowledge about that.
Okay.
Hey, Denise, this is Kayla. Can I comment on that really quick?
Yes, please.
So you're right that at the in the past couple of years, the USGS had not made any indication that they would start including an induced seismicity hazard assessment map again. With the change in administration, this has taken this aspect of their hazard mapping has gotten more attention, and there is actually a national hazard seismic model update workshop that starts tomorrow, and Justin Rubenstein will be presenting a short talk there about their plans to start incorporating induced seismicity into the hazard model again. And then also I should say that we are in discussions with our induced seismicity team within NRAP to work with the induced seismicity team at the USGS for hazard model purposes.
Well, excellent. Thank you, Kayla.
We have another question from Jorge in the chat. What is the most important issue to consider when de-risking CCS projects? And how would we explain these to insurance companies to engage them?
Oh my gosh, the most important, that's like, which is your most favorite child? I mean, they're all equally important. But, you know, honestly, I think one of the things we're starting, and Sherilyn kind of alluded to this, I think one of the things that is becoming more important in our, you know, just in our cultural climate here is to make sure we get stakeholder engagement and acceptance, that the perception of risk is sometimes different from the actual risk. So that even if something is, you know, maybe due to, you know, all different plans and engineering, that the risk is, you know, within, you know, a typical risk that a stakeholder would be comfortable with. If they perceive that that is not the case, then they are not going to be moving forward with the plan. And you know, like, we need local stakeholder engagement, understanding, and ultimately acceptance of the project. And that's again why we put outreach and communication so high in our, you know, in our steps. It essentially encompasses everything. That the technical part is just as important as the non-technical communication part. And that's, you know, the climate that we live in. I think we need to be realistic about that as we move forward, and take that into consideration early and often, and make sure that everybody feels heard, that they feel like they have a way to voice their concerns, and that their concerns are being taken seriously and addressed.
Siraj is asking, what are the key differences between assessing induced seismicity risk due to geologic sequestration, geothermal, and water disposal?
Yeah. So some of the differences are, when we're looking at large-scale geologic carbon sequestration, so the issue here is that, taking a step back, why are we doing this? We need to reduce the amount of atmospheric carbon that's currently in the atmosphere. In order to do that, we need to take a large amount of carbon and make sure that it doesn't stay in the atmosphere, that it gets sequestered into the ground. So just the volumes we're talking about are significantly different. And so that large scale part is, one of the bigger differences. And the fact that, just based on how we may move forward when thinking about large scale reservoirs, there may be different operators, working in the same region. And we see, a little bit of that in the oil and gas industry, for instance. In terms of engineered geothermal systems, it's a relatively smaller reservoir that we're talking about. There's usually just one operator at a time working at any one particular field. So some of the insurance and liability issues are going to be different there as well. And then, looking at, so obviously the size and the volumes are going to be different, for these different applications. And the injection rates could be different as well.
Denise, as part of your outreach communication, do you plan to engage the investor community and the insurance industry about this recommended practice? The reason I'm asking is those are really key when you're looking at large-scale geologic carbon storage projects. If the insurance company says, I do not understand your risk, I'm not going to provide insurance for you, or I'm not going to fund you. This is one of the biggest challenges to CCS developers, being able to really communicate some of these technical risks to a non-technical community in the insurance industry, in the investor community. So are there any plans to really engage those communities around this recommended practice?
Yeah, that's it.
I'm sorry,
Go ahead.
I just wanted to step in just for a second. Yeah, we do have a recent charge from headquarters to begin to make that tie between the quantitative risk assessment that we focus on and the liability piece. And I think so that's something we'll be looking at going forward to ensure that we're supporting, the deployment goals of the program and trying to help with that communication piece that you're talking about. Sorry, I didn't.
No, that's perfect. Thanks, Bob.
We have 1 minute. Any last questions?
Okay, well, thank you everybody for attending. I really appreciate the discussion, and it's like if anybody has any questions, we'd be happy to discuss offline. Maybe send out a link to this presentation. I know it's being recorded, and send out a link to where the documents themselves reside, for instance, or anything else.
Thanks for the presentation. It was informative.
Thank you.
Thank you so much.
Thank you.
Yeah, thanks very much, Denise. Really excellent presentation. Yeah, thanks.
Thank you very much.
Thank you, everyone. Have a good day.